The universe is not gentle, it is precise. Gravity sculpts stars, bends light, and breaks our intuitions. At the extremes live three ideas: black holes, white holes, and wormholes. Ideas that challenge causality and distance. Black holes are real, observed and measured. White holes and wormholes are hypotheses, elegant math, no evidence yet. This film separates evidence from speculation, with clear language and firm footing. We begin with what we know, then we test what we imagine. From tested gravity wells, black holes, to hypothetical tunnels through spacetime, step into the dark. Precision will guide us. Massive stars die. Gravity wins. When fusion stops, the core collapses. The outward push is gone. Gravity crushes inward. A black hole forms. The remnant shrinks relentlessly, compressing matter beyond known physics into a point-like singularity that violently warps spacetime. Its outer layers explode as a supernova, briefly outshining a galaxy. Around the core, gravity curves space-time into a deep, inescapable well. The edge of that well is the event horizon, the true point of no return. Think of a river racing toward a waterfall. The current intensifies near the brink. The brink is the horizon. Beyond it, escape is impossible. For black holes, the current is gravity, and the boat is everything, even light. Cross the horizon, and you're trapped, spiraling inward toward the singularity. Black holes span vast scales, stellar mass, a few to a few dozen suns, scattered across galaxies like the Milky Way. Intermediate mass, the bridge, rare, but mounting evidence. Supermassive, millions to billions of suns anchoring galactic centers. Ours is Sagittarius A star, over 4 million solar masses. Some even reach billions of suns in distant galaxies. Evidence is growing for intermediate mass black holes, bridging the stellar and supermassive families, rounding out the cosmic taxonomy. How we classify them is surprisingly simple. The No-Hair theorem says 3 numbers define a stable black hole: mass, spin, and electric charge. Everything else is erased. All other details of the matter that fell into it, whether it was made of stars, gas, or old spaceships, are lost forever. This elegant simplicity is what makes them such pure objects of gravitational study. They are the universe's ultimate information shredders, reducing all the complexity of the world into 3 basic numbers. This simple exterior hides an interior that remains one of the greatest mysteries in all of physics, a place where our current understanding of the laws of nature completely breaks down. Since black holes are, by definition, black, we cannot see them directly. They emit no light of their own. So how do we find these invisible monsters lurking in the cosmic shadows? The answer is that we look for the profound effects they have on their surroundings. A black hole's immense gravity acts like a cosmic puppet master, pulling on the strings of nearby stars, gas. We do not see black holes, we see their effects. Stars orbit voids with invisible weight. Matter spirals in, heats and shines, especially in X-rays. Gravity bends light itself, gravitational lensing. It draws rings, arcs, and echoes. Arcs, rings, echoes. 2019, the Event Horizon Telescope stitched Earth's radio telescopes into one eye on the sky. It targeted M87, resolving a bright ring of superheated gas. At the center, a dark shadow, the predicted silhouette of a black hole's event horizon. Theory met image, prediction confirmed. 2015, another window opened. LIGO, the Laser Interferometer Gravitational Wave Observatory, made the first direct detection of ripples in space-time, signals from two stellar-mass black holes spiraling together, merging in a violent burst, 1 billion light-years away. Soon, Virgo joined the hunt, and since then, LIGO and Virgo have logged dozens of mergers, turning the dark into sound. Together, images and waves reveal black hole masses, spins, and environments. Masses and spins. Result, images, waves, and dynamics. The dark turned measurable. Near a black hole, time slows relative to distant clocks. This is not a metaphor. As you approach the horizon, your seconds stretch compared to a faraway observer. This gravitational time dilation is a core prediction of general relativity. Hover just outside the event horizon and your ship's clock ticks far slower than Earth's. From your perspective, everything would feel normal, but to friends far away, you'd appear to crawl in slow motion. Return after hours by your clock, and decades or centuries may have passed on Earth. This isn't fiction. Starlight near Sagittarius A is measurably redshifted by gravity. Time there runs slightly slower than it does for us. For years we thought nothing escaped. Then quantum effects added a twist. Hawking radiation. Stephen Hawking showed that black holes can emit faint radiation by combining relativity with quantum fields. At the horizon, quantum fields fluctuate, letting the hole slowly bleed energy. So black holes are not entirely black. They radiate slowly. Hawking radiation. An evaporation of mass into light. Think of virtual particle pairs popping up near the horizon, borrowing energy for an instant. Sometimes one falls in while the other escapes, stealing a tiny bit of the hole's mass energy as it flees. For large holes, evaporation is glacial, timescales far beyond the universe's age. A solar mass black hole would outlast the cosmos by an unfathomable margin. But tiny primordial black holes, if they formed after the Big Bang, could evaporate much faster. Their finales might be brief, high-energy flashes of gamma rays. General relativity allows a mathematical mirror, the white hole. Matter only leaves, nothing enters. A white hole is a region of space-time that cannot be entered from the outside. Instead, it ejects matter and light into the universe. Think of it as the time reverse of a black hole. Its boundary is an event horizon, of the past. Anything inside is destined to be expelled. Nothing from outside can cross in. Observation? None. No astrophysical evidence to date. Telescopes reveal sinks, not fountains. Why so absent? Instability. The slightest disturbance triggers collapse. Even stray photons or particles would doom it. In a universe filled with radiation, survival is unlikely. Models suggest it would rapidly become a black hole. Nature prefers sinks over fountains. White holes remain elegant mathematics. Fascinating, yet unconfirmed. For now, they mark the edge of possibility. Physicists conclude white holes would be incredibly unstable. According to theory, even a single stray particle approaching a white hole could trigger instability. Its energy would quickly disrupt the horizon, likely collapsing the white hole into a black hole almost instantly. In a universe filled with the cosmic microwave background and ambient radiation, stray particles, and light, a white hole would be short-lived, unlikely to survive for long. This fragility may be why we see cosmic sinks, black holes, but no fountains. Still, some quantum gravity models revive white holes through a proposed bounce. To address the black hole information paradox, they suggest black holes may not live forever, but undergo a quantum transition, where the collapsing core rebounds instead of ending in a true singularity. Over immense timescales, the remnant could age into a white hole phase. In that case, matter and information might eventually re-emerge. These ideas, explored in approaches like loop quantum gravity, remain hypotheses awaiting evidence. A wormhole is a tunnel in spacetime, an Einstein-Rosen bridge. In general relativity, it's a solution linking two regions, first derived from Einstein's equations in 1935. Think of it as a curved shortcut carved by gravity's geometry. It connects two separate points in space-time. In principle, it could link Earth's neighborhood to Andromeda, or even bridge to another universe in some models. The idea emerges from the same GR solutions that predict black holes. But the original bridges were non-traversable, a throat that pinches off. The central problem is stability. Most wormhole geometries collapse almost instantly. They close too fast for even light to get through. Keeping one open would require unusual stress, energy. Physicists call it exotic matter, with negative energy density and negative pressure, effectively anti-gravitational, holding the throat apart. We have never observed such matter in nature, so theory permits the geometry, but traversability remains unproven, elegant on paper, elusive in reality. EPR suggests a link between quantum entanglement and tiny wormholes. In this view, two entangled black holes are joined by a microscopic, non-traversable bridge, about information, not travel. It doesn't permit faster-than-light travel or messaging. Gravity, space-time geometry, quantum information. Active research is testing these ideas with theory and simulations. Traversable wormholes would require exotic matter. Such matter would have negative energy density to hold a throat open, and we haven't found it. Could we detect a wormhole if one existed? Search strategies focus on odd lensing and unusual stellar arrangements. For example, stars seemingly displaced across a galaxy by a hidden shortcut. Or gas streams appearing where no local source explains them. A wormhole mouth could imprint distinctive gravitational lensing patterns, producing light rings and arcs unlike a standard black hole. In principle, arrays like the Event Horizon Telescope could tell them apart. No confirmations yet. Ongoing surveys are setting increasingly tight constraints. For now, wormholes remain theoretical, awaiting clear, reproducible evidence. Here is the ledger. Black holes, observed, weighed, and imaged, shadows photographed, stars tracked, mergers heard, established physics, white holes and wormholes, elegant mathematics, no detections. They remain speculative. Theory awaits evidence. We separate data from desire, and keep testing. Onward. White holes are likely unstable, time-reverse black holes that cannot survive. Traversable wormholes would require exotic negative energy matter, that keeps them firmly theoretical for now. Yet both sharpen our questions about gravity and quantum information. They mark the boundaries where our models succeed, and where they may break. So what can we test next? Upgraded interferometers will refine black hole masses and spins. Next-generation telescopes will map their environments in greater detail. Together, these tools may expose subtle deviations from general relativity, or strengthen it by ruling out alternatives. Either outcome moves science forward. Progress here is methodical, cumulative, and test-driven. Evidence leads, theory follows. As capabilities grow, our questions become more precise. We will compare cleaner data to sharper models, tighten uncertainties, and hunt for signatures that distinguish black holes from wormholes. Keep asking better questions and let the evidence decide. Black holes are fact. We can measure their power. White holes and wormholes remain unproven. The frontier is where confidence ends and curiosity begins. Follow for clear, evidence-first explorations of the cosmos.